Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. Unbalance is one of the leading root causes of machinery failure, and this program unveils the keys to successfully perform single and two-plane balancing on common industrial equipment, such as fans, pumps, and motors, to reduce machinery failure and increase uptime. You will be able to use the tips and techniques presented here to confirm machinery unbalance conditions using spectral and waveform data and phase data to avoid some of the common problems associated with field balancing. You will learn the meaning of balancing terms such as weight planes and measurement planes, trial weights and trim weights, heavy spot and high spot, influence coefficient, and unbalance. First, let's take a look at unbalance, its causes, and methods of determining an unbalanced condition. Unbalance is the condition when the center of mass is not the center of rotation. This uncentered mass causes one side to be heavier, and centrifugal force pulls on the system, causing it to move or vibrate. Common causes of unbalance are voids in castings, eccentric components, poor manufacturing tolerances, improper assembly, broken or missing parts, loose parts, thermal distortion, foreign matter lodged in the rotor, a buildup of process material falling off, component wear due to process materials, and on pumps, wear due to cavitation such as on these two impellers. Whatever the cause of the unbalance, there's some concepts you need to know. One is the effect on an unbalanced amount due to centrifugal force and changes in speed. For example, a 44-inch diameter fan is turning at a speed of 2,220 RPM and has 1 ounce of unbalance on the rim of the fan. The effect due to centrifugal force is similar to the force on a ball in a stocking as it is swung in a circle. The force pulls out on the stocking, causing it to fly away from the center of rotation. If the stocking is swung faster, the force pulling it away from the center of rotation increases dramatically. Due to centrifugal force, this 1 ounce of unbalance has an effective weight of 192 pounds, which means that this 1 ounce puts an additional load on the rotor of 192 pounds. The equation that describes this has a squared effect with respect to speed. This means that if the speed is doubled, the effect of the unbalance is increased by a factor of 4. In our example, doubling the speed to 4,440 RPM would increase the effect of this 1 ounce of unbalance from 192 pounds to nearly 800 pounds. If the machine were slowed to 1,110 RPM, the effect of the unbalance would be reduced to less than 50 pounds. At the normal running speed of 2,220 RPM, centrifugal force increased the effect of the unbalanced weight over 3,000 times to equal 192 pounds. Speed, however, is not the only factor that can influence the effective amount of unbalance. The distance the unbalanced mass is from the center of rotation changes the unbalance amount. For example, this 1 ounce of unbalance is 22 inches from the center of the rotor and is called 22 ounce inches of unbalance. If the weight were moved halfway in to 11 inches from the center, the effect would only be half as much, 11 ounce inches of unbalance. The effect of a balance weight can be calculated as the distance from the center of the rotor times the weight amount. So at an 11-inch radius, 2 ounces of weight is required to equal 1 ounce at a 22-inch radius, or 22 ounce inches. This method is often used to describe the amount of unbalance in units of ounce inches or gram centimeters. This concept of the effect of centrifugal force and speed needs to be understood. A second concept is the effect this additional weight has on bearing life. Notice that in this formula used to calculate bearing life, there is a cubed effect with respect to load. The actual rotor weight of our example fan is approximately 1,000 pounds. The rated bearing capacity is 20,000 pounds, and the calculated life is about 60,000 hours. When we add the 192 pounds from the effect of the unbalanced weight to the actual rotor weight and run the equation, the result is approximately 35,000 hours. The life lost due to the 1 ounce of unbalance is 25,000 hours, which is 42% of the original life. These two concepts, the effective speed and centrifugal force on any unbalance in a machine and its effect on bearing life, point to the need to perform quality balancing. When a vibration sensor is mounted on an unbalanced machine, the unbalance will bump the sensor once during each revolution of the shaft. Recall from another program, Introduction to Vibration Analysis, how a machine's vibration generates particular waveform patterns, and how the waveform is transformed into a spectrum where each peak in the spectrum represents actual movement in the machine. Unbalance generates a bump on the sensor once each revolution of the shaft, so we expect a peak in the spectrum at a frequency equal to shaft speed. Since centrifugal force is pulling the mass outward from the center of rotation, we expect a spectral peak in the radial directions, that is, the horizontal and vertical directions. However, there should be very little motion in the axial direction caused by this unbalance. An overhung fan can be an exception to this rule. But in general, if the axial measurement at shaft speed approaches the amplitude of the radial readings, look for another problem instead of unbalance. The radial measurements may have other peaks present, but the turning speed peak must be dominant before balancing will substantially affect the machine's condition. The waveform data will have a dominant sine wave, and even if it is very busy with other energy present, there should be an underlying sinusoidal shape. Depending on the mounting, the machine may have more freedom to move horizontally than vertically, or just the opposite. But if one radial measurement is more than 3 times the other one, suspect another problem such as resonance and perform tests to check the phase. Remember that unbalance always causes a 1 times peak, but not all 1 times peaks are due to unbalance. There are many machinery conditions which generate 1 times peaks. Some of these are misalignment, a bent shaft, an eccentric rotor, mechanical looseness, some electrical faults, resonance, and on belt-driven equipment, an eccentric sheave. A diagnostic tool that confirms an unbalanced condition is phase analysis. Steps to use phase to diagnose machinery conditions are covered in another program, Detailed Phase Analysis, where we pointed out that phase is a relationship between 2 events, and that the phase we measure is actually the timing between pulse at a mark on the rotor to the peak of vibration. A phototach, such as this infrared model, sends a beam to the rotor. Reflective tape on the rotor sends a signal back to the phototach each time it passes. The phototach then sends a pulse to the analyzer, which measures the time between pulses to calculate the RPM. The analyzer monitors the vibration sensor and measures the maximum vibration at this RPM. Now the analyzer compares the timing between the 2 signals and displays the difference as an angle in degrees. This phase angle is used to locate the heavy spot on the rotor. This method of measuring from the tach pulse to the peak of vibration is called true phase. All CSI instruments use the true phase method. Measuring from the peak of vibration to the tach pulse is called reverse phase. You must know which method your instrumentation uses. To use phase measurements as a diagnostic tool, keep the phototach stationary and roam the machine with a sensor comparing the instantaneous phase angles, which indicate the movement of the machine with respect to the phototach. When the sensor is moved from the horizontal to the vertical position, we expect a corresponding change in the phase reading of 90 degrees plus or minus 20 degrees. If there is no change, or a change of 180 degrees plus or minus 30, it indicates a resonant condition. We know that if we trace the phase during a coast down, as the system goes through resonance, there is a 180-degree change in the phase with a resonance at 90 degrees. So if the change is 0 or 180 degrees, it indicates a resonant condition. Perform other tests, such as a bump test, to determine which direction has a resonant condition at shaft turning speed. Then correct the resonant problem before balancing the machine. When making the phase measurements, monitor each point long enough to ensure the readings are steady. If there is mechanical looseness, the readings may bounce all over. If there are other frequencies spaced closely to the turning speed peak, the phase may slowly rotate the full 360 degrees. The instantaneous phase readings must be steady within a 30-degree range before a successful balance job can be performed. The phase must also be repeatable from startup to startup. Non-repeatability may be caused by loose parts that may lodge in different places on each startup. These loose parts may in fact be the source of the unbalance. If liquid from steam condensation or a process fluid is entrapped in a drum, it will move to the bottom when the machine is stopped, and when spun up to running speed, may accumulate at different locations, causing different unbalanced characteristics and non-repeatable phase readings. Fine particles such as sand and rust will generate similar results. Ensure the condition is unbalanced by checking the spectral data for a dominant 1x peak with a corresponding sine wave in the waveform data. The phase should be steady at each measurement point. A movement of the sensor 90 degrees should produce a corresponding change in the phase, and the phase measurements should be repeatable from startup to startup. Before beginning the actual balance procedure, preliminary steps must be performed. One is to perform a series of pre-balancing checks, and the other is to identify the complexity of the balance job, defining measurement locations and correction weight locations. The 7 pre-balancing checks include vibration measurements, phase readings, determining the resonant frequencies, a walk-around inspection, checking for a bent shaft, cleaning the rotor, and on belt-driven equipment, checking the sheave runout. The vibration measurements should include a horizontal and vertical at each bearing location and an axial reading. Verify that the dominant energy is at shaft turning speed and that the waveform has a sinusoidal pattern. Use the horizontal to vertical rule to check for possible resonant conditions. The axial measurement should be less than the radial measurements. Record the phase measurements for each measurement point. Check to make sure they are stable within a 30-degree swing and that there is approximately a 90-degree shift from the horizontal to the vertical position at each bearing location. Determine the resonant frequencies by performing tests for resonance, such as a bump test, or monitoring the peak and phase of the machine during a coast down. The running speed of the machine should not be within 15 to 20% of a resonant frequency. During the walk-around inspection, check for loose mountings, broken bolts, cracked or broken wells, cracked foundations, loose parts, accumulated process fluids or solids. Structural cracks in wells or foundations may seriously affect the machine's integrity, causing unstable phases and changing the resonant conditions of the machine. Don't underestimate the value of this walk-around inspection. Many serious problems have been found and many unnecessary balance jobs avoided due to a thorough inspection. For example, an analyst was called to balance a fan that conveys aluminum chips from a milling process. The vibration data indicated a severe unbalance, but the analyst did a walk-around inspection anyway and found this ball of aluminum chips lodged in the fan. He balanced the fan using a good pry bar to remove the ball. Use a dial indicator and check for a bent shaft. A severe unbalanced condition can cause a shaft to bend, but it is very difficult to correct a bent shaft by balancing. Clean the rotor before balancing. Air circulation fans can become partially blocked due to the buildup of dust and oils and cause excessive vibration due to airflow problems. Fans that move solid particles tend to accumulate the material, which falls off unevenly, causing unbalance. Each stop and start of the balancing process can cause more material to fall off, changing the unbalanced location and making each attempt futile. A sheave with excessive runout can exhibit characteristics of unbalance on a machine. The eccentric tolerance on the sheave combined with belt variations may be as much as a 1/4 inch per foot of sheave diameter. Replace sheaves with excessive runout. Do not rule out the sheave as it may be the source of the machine's unbalance. Use these 7 pre-balancing checks to maximize the effect of balancing and avoid going in circles. Don't try to solve other problems through balancing. The complexity of a balance job is determined by more than just the design of the machine, but includes the vibration and phase characteristics as well as the balance specifications. The simplest balance job is a single measurement point, single plane balance. A balance job is defined by the number of weight planes used for correction. A weight plane is a cross-section through the rotor onto which balance corrections can be made. This rotor kit has one weight plane where balance weights can be added or removed. But this rotor kit has 2 weight planes where balance weights can be added or removed. So by its very nature, it has the possibility of being more complex. There must be at least one measurement point corresponding to each weight plane in order to make the calculations for correction weights. But you may want to make more than one measurement point for each weight plane to ensure that lowering the vibration in one direction does not raise it in another. On this single plane rotor kit, using only one measurement point, the effect of additional weights is measured at this point, and the balance procedure continues until this one measurement point is within tolerances. On this 2-plane rotor kit, however, we must place weights so that all measurement points are within tolerances. If only one measurement point is to be used at each weight plane, select the direction that has the highest amplitude of unbalance. This will typically be the horizontal direction for machines with vertical hold-downs. Although there are 2 planes for placing correction weights, this system may be able to be balanced as a single plane system. It depends on the characteristics of the unbalance. Let's use these wheels on a shaft as an example. If the wheels are the weight planes, and each plane has equal amounts of unbalance in line with each other, then as the wheels are spun up, the entire shaft will move together, causing the phase angle to be the same at both ends. When stopped at a frictionless mounting, the unbalance swings to the bottom. This type of unbalance is called static unbalance because it is unbalanced when it's stationary. Static unbalance can usually be corrected in a single plane. Even when there are 2 weight planes, the correction weight can be divided in 2, and one part placed on each plane at the same angle. A statically balanced rotor will stay in any position when it is at rest. Another type of unbalance may be statically balanced so that the rotor will stay at any position when it is at rest, but when it is spinning, it exhibits unbalance. This is because each end of the rotor is unbalanced. The unbalance amount is the same at each end, but in the opposite direction, so that the rotor is balanced while it is still. This type of unbalance is called couple unbalance. The phase data will indicate the ends are moving in opposite directions. Couple unbalance must be corrected with equal amounts of correction in 2 planes, but 180 degrees opposite each other. Any combination of static and couple unbalance is called dynamic unbalance. The phase data from end to end could be any combination and will usually require correction weights in more than one plane. Manufacturers sometimes provide specific locations for adding correction weights, and these must be used. Some machines have only one plane for making any balance corrections, such as this overhung pump, where the corrections must be made at the impeller end. This narrow center hung fan can be balanced in a single plane, but this wide center hung fan will probably require 2 planes. The rule of thumb is that when the width to diameter ratio is 1:4 or greater, it can usually be balanced in a single plane. A long shaft, such as a drive shaft or jack shaft, usually requires 2 planes. Add the correction weights about 25% of the distance from each end. Axial flow fans should not have the correction weights attached to the blades in any position that will affect airflow dynamics. To avoid changing the stiffness and resonance of the blades, don't put weights on the blades unless there is a balance ring provided for attaching weights. Most axial flow fans require weight corrections near the hub. Use the pre-balancing checks to confirm unbalance is the problem and determine whether single or 2-plane balancing will be required. Check the manufacturer's recommendations for weight planes and weight placement. Balancing is a straightforward procedure, and when the pre-balancing checks have been completed and other problems corrected, the balance job can go smoothly. Here we will take a brief look at the balancing steps and the principles of how balancing works. There are essentially 4 steps to the balancing procedure. The first step is to measure and record the initial unbalanced data. This unbalanced data includes the vibration and phase information at 1 times shaft turning speed as well as shaft RPM. This initial data is referred to as an as-is run or reference run, and it must be done for each measurement point to be used in the balance job. This step provides data for comparison for the next steps. The second step is apply a trial weight in the weight plane and measure the results. The trial weight is a known amount and is placed at a known location on the rotor. This trial weight should not be permanently attached because it is used only to see how the system responds so that calculations can be performed for a correction weight. The third step is to remove the trial weight and attach the calculated correction weight, then measure the results. Check these measurements to see if they are within tolerances. If the measurements are within tolerances, you are through. If they are not within tolerances, then continue to step 4. The fourth step is to perform trim balancing. Trim balancing uses smaller amounts of weight and each one is left on the rotor. Continue trimming in until the results are within specs. Since the measurements made during balancing are phase measurements, having an amount of vibration and the location or direction it is from the reflective tape, they can be displayed as vectors. A vector is a graphical representation of amount and direction. A vector can be any amount and direction. For example, on a map we could draw a line from Nashville, Tennessee to St. Louis, Missouri. Since it represents a distance or amount of 330 miles and a direction northwest, it is a vector. Another vector could be drawn from St. Louis to Indianapolis, Indiana, representing a distance of 250 miles in a direction of east-northeast. These vectors can be mathematically or graphically added together. For example, these 2 vectors sum to equal a vector from Nashville 335 miles north to Indianapolis. The balancing phase data can also be displayed graphically as vectors since the measurements have both amount and direction. The amount is the measured vibration due to the unbalance within the machine. The angle helps us locate the unbalanced mass so we can know where to place the correction weights. The amount and direction can be drawn on a polar chart, which has the 360 degrees of a circle, and the spacing of the lines can be set to any scale needed for your balance job. Here we will let each space represent a vibration amount of 1 mil. Now we will record the initial vibration and phase data of the machine before we actually begin the balance job. This data is the as-is or reference run data. The initial reading is 6 mils at 90 degrees. 90 degrees is here, and 6 mils is here. A line from the center to this point is the vector that represents the initial unbalance in the machine. Label this vector R for the reference vector. The goal of the balancing procedure is to draw